slope stability. We also have Mr. Devmallo Roy, manager at Budget Groups, who will be discussing railway embankment and transportation geotechnics. Along with that, Dr. S.S. Kumar, assistant professor NIT Patna, who will cover the ground improvement techniques. After that, there will be online test and feedback and the valedictory session. So, may I now invite our distinguished speaker, Professor Arindam Day, to lead the session. Over to you, sir. Please, sir, please.
Okay, thank you, Krishna. Let me share and just check if it is visible to all. It is saying host disabled participant screen sharing.
Sir, I have done this, right? So, right now,
yes. I hope you are able to see, right?
Yes, sir. I'll make it full screen. Okay, sir. It's okay, sir.
Is the pointer visible?
Yes, sir. It's visible.
Oh, okay. Great. So then let's start. So good afternoon, all. So hope all of you had a good lunch and you are ready and relaxed to go ahead with our session today. So in this session, as I mentioned earlier, in the previous session, we talked about the seismic geotechnics. So this session will be more about the rock slope stability. And in this process, I will be talking mainly about this jointed rock slope. So which provides a very unique scenario and a unique problem to deal with. It's not like a regular problem which we deal with the landslides and slope stability, or even in the rock slope stability. The joints creates a lot of nuisance, and as geotechnical engineers we have to deal with such problems. So I will talk about such topics which are relevant to the jointed rock slope stability analysis. So in case when we talk about landslides, we understand that it is a very serious natural calamity, and this landslide basically belongs or creates an umbrella which covers many type of devastating phenomena which occurs involving rock, earth, debris, and all around the world. So this is a publication from Nature 2012. So this gives an idea that within only 6-7 years, from 2004 to 10, how many landslides have taken place all around the world. And you can very well understand that we are in a very, very vulnerable zone. India, China, the Southeast Asian countries, the western coast of South America, North America, Panama, all these places are severely affected by landslides. Italy, France. So wherever we have these mountainous terrains, so we are basically looking into the potential threat from landslides. Mind it that this map does not include the earthquake-induced landslides. So many of the other regions would have been covered by those white dots. If we look into the Indian region, so we understand that it gets mostly focused on the Garhwal Himalayas, Uttarakhand, Himachal, and the upper reaches. In the northeastern part, Sikkim, all the northeastern states, Kerala, some parts of Maharashtra. But these are again only a few. There are many other points which can again completely engulf all these areas what I'm showing. Some examples which we come across the news, the literatures, the documents, the media articles, and these all sorts of landslides and catastrophes create a lot of havoc, not only to the infrastructures, but also to the lives and economy. And most of the cases, if not all, most of the cases, finally, the population growth, the urbanization, development in the difficult terrains, that one way or the other cause such landslides. And then over the years, the trend of fatalities, the number of fatalities are keeping on increasing. And as geotechnical engineers, we are supposed to look into some of these issues and problems and try to avert as much as possible. We cannot stop it from happening, but we can definitely take many necessary steps where we can minimize its effect. But those being discussed mostly in terms of soils and earth flows, mud flows. Now, when we come to the rock slides, now this presents a very unique feature. Now, in case of soils, mostly we consider them to be homogeneous or heterogeneous in some of the advanced context. But in rock, the feature of discontinuity presents a very complex structure to be handled. And frankly speaking, the fundamental ways of slope stability analysis, how we handle in case of soil or earth slopes, many a time not really work for the rock slopes, especially when the discontinuity and joints are present. Just to show a few examples. So this is a jointed rock. You can see it's a huge mass of batholith. So we have intact rocks, but through the intact rocks, the joints are passing. Now, if you have to analyze such cases, so you have to take into consideration both the characteristics of the intact rock as well as the joints, which we generally do not conduct for slope stability analysis when we do for the soil or earth slopes. And this is only a rock with intact rock with two joints, which you can visualize. It can increase in complexity when we talk about the joints, their intersections, and as well as the bedding planes, which all comes from the formation of the rocks, upliftment of the rocks during the prehistoric era. So these interactions now create a very complex situation. So neither it is a continuous media as soil, nor it is a complete discrete media as two different elements. So it lies somewhere in between. And whenever engineering problem comes which does not follow the binary rule, either this side or that side, then the problem keeps on increasing for us. This is another such jointed system, which we call as a cascading book fall. So if you keep the books in the rack of the library or your almirah, and if you just push them, they just drops over one another and take such shape. Now, such type of jointed rock system are present in many places, creating difficulty for us that how we should analyze them. Our normal slip circle method, Bishop's method may not be able to handle all these situations. You can increase the complexity by placing the joints more closely. So here you can see closely spaced joint system, and imagine that you have to solve it through a friction circle method. It's virtually impossible because each of these joints might give a shear plane or might emerge into a failure plane, and it may not follow a slip circle type of definition. Then comes folds. So you understand folding and faulting, the ways the Himalayas are built by upliftment due to the pressure from both the sides, and that leads to the depositions to bend over areas, anticlines and synclines are created, cleavages are created. Now, if such situation arises, so already there will be planes which will be weak in nature, but which will not really like a slip circle or a non-circular slip mechanism. So it will be a very complex mechanism to deal with. And then comes a very difficult subject to handle, which we do talk about in soil mechanics, but do not literally use that much for slope stability analysis, but which we cannot avoid for rock slope stability, that is anisotropy. Now, because of the presence of these joints oriented at various directions, the strength actually varies with the direction. So the anisotropic strength, if we really have to incorporate into our understanding, it is not an easy cup of tea. So we have to take course of samples of rocks from various locations, and then we have to do anisotropic strength test to figure out how, with the change in the inclination of the joints, change in the direction of dip of the joints, the strength changes. And if we want really to understand them, we have to do those exercises and bring them into our numerical models, which is not really very easy. It is taxing, it is computational, it is resource crunching. So all those things are somewhat hindering to move ahead to our next steps. So when we talk about rock slope failure, as I was mentioning, it is not really, as we understand, a soil slope failure. Here the mechanism remains a bit complex. So when we talk about rock slope, you can see this picture. So in general, these are 4 types which I have shown here. There might be compound failures and other different types as well. These are the common ones which we literally handle. There might be a failure through a single joint. It can be a planar failure. There might be multiple joint sets existing that will lead to a wedge failure. So a chunk of material from 2 sets of joints will come out. There also might be cases where circular or non-circular slip type of failure happens as in the soil for specific cases. And then there can be toppling failure as well. So big pieces and chunks of rocks just falling over its toe or overturning over its toe. So understanding that all these different mechanisms can happen, a single way direction of thought as we do for soil slope stability analysis might not be enough. For example, here are some pictures to show. So you can see that this particular slope has 2 or 3 sets of joints. One is here, another is inclined in other direction. So they are crisscrossing and forming a zone which is called daylight. So daylight means which is the exposed zone of the jointed rock slope and which can have a tendency to fail under specific scenarios. So if such type of planar sections exist, so a sliding type of failure might be occurring in such slopes. In those cases, you can do a translational failure analysis or a sliding failure analysis, as sometimes we do for soil mechanics for very stiff type of material. Now you can have 2 joints literally crisscrossing with each other. So there will be a piece of material which can come out, which is remaining attached to 2 sets of joints. And this intersection daylight can release the material during its specific condition. So this type of failure is considered as a wedge failure. And here also you can apply some basic mechanics and then you can find out whether one particular wedge will come out or not. But then problem starts as more and more joints starts to intersect. So as more number of joints intersect with each other, the formation of intermediate chunks increases. They can just fall over their toe like a topple. So they just overturn about their toe, and that can lead to a toppling failure, which really we do not do in any type of soil mechanics slope stability analysis. As I was mentioning, there might be cases where there will be circular failure or non-circular failure, but more alike soil mechanics type of slope instabilities. When the rock is soft or whether it is highly fractured or the spacings are so close that they construct a homogeneous rock mass, then we may see such type of failures. But then the solution of such failures is not as easy as we do for the soil mechanics, because here grains or granules of rock will be actually falling down together. So it is more like a particle flow which has their own impact and momentum during the flow, and that has to be addressed during the stability analysis. So although it looks similar in visualization like the soil slope stability, we may think that we will simply do a circular failure analysis, but it is exactly not so. Here we have to deal with the particle flows, which we generally do not consider in soils because the soil particles are much lesser in sizes. Here we have good size, big size particles all will be coming down together, giving a apparently circular or non-circular failure surface. So when we talk about rock slope stability analysis, as I was trying to mention, that because of the variations and the existence of different scenarios in the rock slope, which had been constructed or formed over the years, the rock slope stability analysis also has different vistas. We can start from very simplistic qualitative understanding of stability to a more complex quantitative understanding. So we generally divide this rock slope stability analysis into few categories depending upon what we want to do, depending upon the rigorosity we want to achieve with the analysis. We have few conventional methods. Among the conventional methods, We have 2 or 3 different types I will mention. And over the time, we have developed these numerical methods, which is keeping on developing or evolving over the years. So we are trying to move as close to reality as possible, but it is not so easy, and we are still lagging far, far behind from the reality. Among the conventional methods, we have a method called kinematic analysis, where we do only a force-based analysis to try to get some idea whether there is a potential of failure in the rock slope system or not. So in that case, we do some stereo net plots, we do some friction cone analysis, where we just do some force-based equilibrium. And then we have our conventional limit equilibrium analysis, which I guess all of you are well aware. So whatever we do in soil slope analysis, mostly are limit equilibrium, the Bishop's method, the Morgenstern's method, the Spencer's method, friction circle, all those things are under the umbrella of limit equilibrium. Here also we can use them, but keeping in mind that the failure surfaces might be different. There might be a planar surface, then we have to do a planar sliding analysis. There might be an intersection wedge failure, we have to do wedge analysis. And as I showed, there can be situations which can be apparently visualizing it as a circular or non-circular failure. So there we can do slip surface analysis. This falls in the simplistic part of the assessment. In the numerical method, now we can do continuum modeling. In the kinematic or limit equilibrium analysis, there is no concept of deformation. You either balance the force, or you balance the moment, you balance the stress, or balance moment and stress, but never deformation comes into picture. So conventional methods are more like rigid body analysis, where there is no deformation. But we very well understand all our geomaterials deform. And if we really do not consider deformation into our analysis, then we might be actually moving away from the reality. All the cases might not be able to be captured. So to capture those cases, we have continuum modeling, where we devise the rock as a continuum system. And then we can resort to the tools like finite element, finite difference, boundary element, meshless methods. And in all these cases, it is a coupled stress deformation analysis. So deformation starts coming into picture. So now deformation will modify the stresses, and accordingly, we can do the slope stability analysis. Going ahead further, if we want to really look into how each pieces of rock are contributing to the stability and what are their influences towards instability, then we go for a method which is called a discontinuum modeling. So in the discontinuum modeling, as the name suggests, here we go to the rock particle level or rock block level and start looking into their mechanics and their interactions. So the methods which we generally use are distinct or discrete element method, where each block and their interaction can be modeled. A discontinuum deformation method, so where we model the blocks, but only in terms of their deformation-based assessment. And then we can hybridize them so that both stress deformation coupling can be done, and we can go ahead with a very advanced discontinuum modeling. So moving from left to right, so we are basically making the things more and more complex. So we are adding complexity into the analysis, but probably that's what it is needed if we want to basically capture many of the real life rock failure cases, especially in the jointed scenarios. So we are increasing the complexity, but that is only helping us to moving closer to the reality. We are lagging far behind to the actual reality, by the way, even as of now. So this entire discussion, what we are going to look into these next few slides, or to the rest of the discussion, the entire discussion will hover around the software, which is called Rock Science. So it is a fantastic software which has many modules, and each of these modules can solve a specific problem related to rocks and soils. It was specifically developed for rock related issues. Now it has been also transgressing into the domain of soil stability or soil instability analysis. So Rock Science is not a free software. Rock Science is a purchasable software, but you can always get some academic licenses, or even student trial licenses are available upon request from your institute ID. Actually, you can request the agency, and for few months or maybe a year, they can provide that upon specific request from the institutional level. So first, we will look into this kinematic analysis, which uses a module of rock science known as DIPS. So here we only try to figure out that whether there is a possibility of translational failure or not, either in a planar manner or through a wedge, and nothing else. We do not go into any further complexity at all. So in this particular case, we have to remember our old geological text where we talk about dip, where we talk about strike, the dip direction, plunge direction, dip angle, strike angle, rake. So all those things related to rocks and their interaction in the geological level, you have to again recall those terminologies. So in the field, you can actually measure the inclination of the rock slopes using an inclinometer from the tangible areas, or you can resort back to the numerical procedure of drawing stereo nets, where you use a reference sphere and then you find out a trace plane through which you can find out whether a joint will lead to the formation of a planar failure or a wedge type of failure. So this stereographic projection is nothing but the representation of these dip, strike, plunge, rake, all these things in a spherical coordinate system. So this is one book, Wiley and Ma, very nice book related to rock slope stability analysis. So there are plenty of examples how different type of failures, whether a circular one, whether a planar one, toppling, whether a wedge failure, how they can be represented in the stereographic projection or the stereo net. So if you get a stereo net, so you will be actually, if you are practiced, you will be able to tell what sort of failure might be possible. Now remember, I'm telling might be possible. Later I will show that this process is actually so simple that it might not always reflect the actual reality, and there might be deviations, but yes, for getting the first-hand idea, this is quite good enough. Problem begins with the fact that when we have rock slope, jointed rock material or rock blocks, there are two types of joints which might be available inside the system. One is called a persistent joint, as the name suggests, and you can see in the picture. These are the joints which traverses all through the block or all through the material. So they are persistently present. Other type of joints might be non-persistent. So there might be some joints inside the system or even in the face of the system, which might not proceed throughout the rock block or the rock chunk. Now, persistent system are still you can able to model. Non-persistent system are difficult to model, even difficult to identify if they are much inside the rock slope. So that really creates a problem that through these stereo net, we can only handle the persistent type of joint sets and not the non-persistent ones. So that's where the kinematic analysis sometimes becomes adequate. But having said that, we always start with kinematic analysis because that at least gives us the first idea whether there will be a planar failure or whether there will be a wedge failure, and then we can move on to further complicated or complex scenarios. The next is limit equilibrium analysis, and the module of rock science which uses this analysis technique is called swedge. So this is more like a wedge type of analysis under friction. So it is a limit equilibrium wedge analysis, and you can use this one for either planar sliding or whether there is a mass of rock which is sliding in the form of a wedge. So wherever there is a rigid mass of rock moving over either single or two sets of joints, so you can use this module swedge in rock science to figure out what will be their stability in terms of the factor of safety. Now, in case of slip surfaces, you can use swedge, but then we say that we can use some other module where we may not get, for swedge does not give so accurate understanding of the factor of safety in terms of a continuum system where we can get a circular type of failure. It is more practicably used for this type of rigid joint failures. As I was mentioning, if you have a very heavily jointed rock system, that can still give a circular or a non-circular slip type of mechanism. But in all the cases, if you notice that all these cases of limit equilibrium analysis, we consider that the mass which is moving is a rigid mass, there is no deformation in the system. So a rigid body moves above the slip surface, whether planar, whether wedge, let's say whether a circular or non-circular one. And the factor of safety against stability, the way we find for our soil mechanics problem, for one slope stability analysis, we get one single factor of safety, which inherently means that the factor of safety remains constant through this entire failure surface. So that is an inherent limitation or shortcoming from the limit equilibrium analysis itself. But if it is a rigid mass, if it is moving, that one having a predefined surface with the same factor of safety is mechanistically correct. Problem starts when joint persistence and spacings are there. So we need to understand more that how spacings and rock chunks in between the spacings interact with each other, whether the joint is a persistent one or not. Now, these are not included in the conventional limit equilibrium analysis. And here, the intricate internal deformation, that is the displacement, the movement, the amount of motion. So those things are neglected, even the fracturing ones. Internal fracturing we cannot handle because, again, of this rigid block assumption. So next, as I was mentioning, we need to move to a little bit more complex scenario in terms of mechanics. So here we consider a continuum modeling where we now include deformation into the analysis, a coupled stress deformation analysis, as we say. So deformation changes the stress, stress changes the deformation, and these two keep on playing to finally figure out what will be the stability or instability in the system. In rock science, you have a module which is called as the phase 2. In this particular module, we can actually represent a fragmented rock or a jointed rock system to a equivalent homogeneous mass. So while doing a continuum modeling, we have to remember that we are still not considering fragments of rocks. Rather, if they are fragmented, we are considering we will represent in some manner this jointed set into some homogeneous set of rocks. So here we move from a jointed model to a rock mass. But how is it different or advantageous from the earlier case? Here we will introducing deformation of each of these blocks, which we could not have done in the earlier two kinematic and limit equilibrium analysis. This method is called as an equivalent continuum method. So we are creating an equivalent continuum system from a discrete system, and that's why this equivalent word comes into picture. So in the equivalent continuum method, when we have to use this, let's say using through finite element, finite difference, or whatever tools, we have to have equivalent rock mass parameter. So you can test pieces of rocks, get their fragmented parameters, but then finally that you cannot use in such model. You have to find out equivalent rock mass parameter, because even though joints are existing in your model, in the equivalent continuum model, although you are drawing those joints through the geometry lines, they are only geometrical inclusions. We are still creating a homogeneous system. We are not really considering the joints actually affecting the system unless and until we do some joint material analysis. In this case, we use a technique of stability analysis, which is called shear strength reduction technique, mostly similar to the stability analysis in terms of what we find as factor of safety. Although here our terminology is not factor of safety, but strength reduction factor. And how is it different? How these two methods are different, I will just show in one of the slides later. So this equivalent continuum method might not be always appropriate to use. So when it is appropriate, if you are carrying out the analysis of rock slopes that are either composed of massive intact rocks, so a huge size single or dual rock system, if they are made up of very weak rocks which can get crushed under load, or if they are heavily fractured rock masses, so that the homogeneous system, this can be as closely achieved as possible. If the system is not homogeneous, if it does not follow these criteria, then you can still use equivalent continuum method. Nobody can stop you from using it, but your results will always be a bit questionable. So as I was mentioning, in this continuum modeling, you can model the entire rock slope and then analyze it through the finite difference method. You can use finite element method. And then through the strength reduction technique, shear strength reduction technique, as I was mentioning, you can figure out through which joint locations the failures will take place. So you can see that it is not really like a slip surface, which we are very keen to see in case of slope stability analysis. Here, failure surfaces develop through those joints, whatever we model in the equivalent continuum method. Now, there have been advancement in the equivalent continuum method as well. You can not only model it as a homogeneous system, you can even model the joints so that you get a better idea than the historic equivalent continuum when it was initially started. I will show through one example. And the latest one, the most complex one, but again, most closer to reality, is a discontinuum modeling of the jointed rock slope, where we now start looking into the blocks of rocks and their interactions and failure. And now this anisotropy created by the joints, the change of strength in different directions, change of shear condition in different directions, which leads to the structural failures, those can be modeled in discontinuum modeling. But imagine that now you have a rock slope which you could have modeled by limit equilibrium or a finite element method. Now you have to figure out how each rock pieces are interacting with each other, and then only you can go ahead with discontinuum modeling. So if you are trying to handle very, very complex situation with discontinuum modeling, again, you have to go back to some assumptions, which again hinders or curtails the exact understanding of the problem, but it gives a fair apparent idea. So for example, here is one such paper you can refer to, Kaintola et al. In 2015. They have modeled through the discontinuum approach, where now they can find out how each piece of this jointed rock system can move, what is the direction of movement, what is their velocity of movement, how long it will take for one block to fall over or move to certain limit beyond which we can say landslide or rock slides have triggered. Those things can be understood. So this is the structure of Petra. And Hudsor et al. In 2004 analyzed the structure of Petra in form of the discontinuum modeling, and they found out that if it fails, how the failure scenario would take place. Here now you can see each of these rock blocks can be located from its initial to its final position, and now the failure is not like a continuum system, it is like a discrete system. Each rock block can be traced from its final position during and after the failure. So here we are using this discontinuum modeling for prediction of the behavior of jointed rock slopes, and two very popular techniques are discontinuum deformation analysis. So it is more like this one, the one which Kaintola did. So here they are not literally detaching from each other, but still it is a deformation taking place in a discontinuum system. Or one can use a distinct or a discrete element method, which is more pertaining to what Hudsor had did, where each rock block movement can be traced. Distinct and discrete are more or less the same, except that in distinct element method, you actually model bigger chunks of rocks. In discrete element method, you can go to the particulate level, which I was once in few slides ago, that you can actually do a particulate level analysis that can be done through discrete element method. So here the challenge increases because the stress strain interactions we have to consider with the incorporation of explicit joints, which means that we have to define all the joints, their material characteristic, their properties, allow one joint to detach from each other or slide against each other independent of the other one. So that's where the challenge becomes more, and we need actually a very sincere effort in the investigation part as well to model such scenarios. Just to mention that DDA, the discontinuum deformation analysis, was invented long back. So these techniques are not new. These techniques are quite old. It was discovered or presented in the 1980s, where isolated blocks are bounded by discontinuities, as in Kaintola. So the isolated blocks are there, they're bounded by discontinuities, and they can model large deformation and rigid body movement. So you can make it as a flexible blocks, rigid blocks. So both these things can be accommodated. Whereas in distinct element method, you can see that this is still older. It is in 1970s, where discontinuous rock mass can be assembled as a quasi-rigid as well as deformable blocks, like what Hudsor did in this particular exercise, where each of these block interaction can take place either at the beginning or after falling down. One block which is interacting with the earlier blocks may not interact further. It starts interacting with a new block system. So all those complexities can happen. And then it is very proficient in simulating very large displacement due to slip or opening or detachment, everything. So here comes that when you slowly move ahead to understand a bit more realistic scenario. So one thing I think it is now clear that we have to explicitly define the joints. And if you are able to define the joints, their properties, then we are moving much closer than what we were achieving through the limit equilibrium method. So there are models, various type of joint models. One such very popular one is explicit joint element model given in 1960s. The development of such explicit joints have been done in metal deformations, composite materials, but slowly we have started using them for this type of jointed rock system as well. Just to mention these elements, the small element 1, 2, 3, 4, what you are seeing here, this is the interface element or the explicit joint element. It is of 0 thickness mathematically. It is a rectangular element having 4 nodes and 8 degrees of freedom. Interesting thing is that this element can be given both normal displacement and tangential displacement, and that can control the movement of these two blocks attached through this joint. And then the interface stresses, that all depends upon the relative displacement between these two blocks, and that is governed by a constitutive relation. So you have to know a little bit of the constitutive relation. One such relation is Hogue-Brown, Barton-Bandis, and many other relations are there. Now, if you are trying to understand that how rock block deformation take place, at one point of time, you have to try to assess whether they will be detaching or not. Now, if they are detaching, you cannot do it like a finite element system where the tangential and normal displacements are always coupled. Here, through this explicit joint element, you can uncouple them, because you can uncouple tangential and normal stiffness, and which will lead to the fact that the shear and the normal deformation will be independent of each other. Now, if they are so independent of each other, there might be a situation where there will be tensile stresses developing, and none of these, and we understand that soil or any geomaterial is weak in tension, the joint will detach. So if the joint normal stress is tensile, so both these stiffnesses during the modeling purpose are set to 0, and that leads to the opening of the joint. So what we were seeing in the Hadzor structure, that one block is detaching, so that type of opening we can actually achieve through this explicit joint element. So relative displacement occurs between these two blocks, and we very well understand the basic concept still remains the same. Due to the relative displacement, if the joint shear stress exceeds the joint shear strength, the failure of that particular joint will start taking place. It does not necessarily mean that the entire jointed rock slope will fail altogether. A very nice example I will show in one of the case studies. So I will basically show two case studies, one for static stability analysis of jointed rock slope, another one is a dynamic stability analysis of a jointed rock slope. For the static stability analysis, I will show you the Sikkim Himalayan case study, which we worked upon for a highway, the Gangtok-Lachung highway passing through North Sikkim. The study area becomes very important, as this is one of the major transportation corridors serving our northern territories and even the border territories. And this area is highly affected by these rock slope failures, rock slides, rock fall, rock topple, everything is present there. And most of the times, these areas get heavily affected by earthquakes. You remember the Sikkim earthquake, the Nepal earthquake later on. Recently, the Tibet earthquake happened. And if not failure has taken place during the earthquake, what happens that during the earthquake, all those blocks get basically shaken up, their strength reduces, and they are ready to fail for some future events. May not be an earthquake, maybe a small hill cut, maybe a small rainfall, and those things are very common in the study area. So we worked on some locations with some of our other colleagues. From some of the published literature, we got some data. We did some experiment there itself. So we took one particular slope. So this is one slope which you can see. This slope was characterized by 3 types of joints, or rather 3 sets of joints. One is joint 1, which is on the visual side of the slope, which is another is joint 2. where joint 1 and joint 2 is forming a wedge, and another is joint 3, which is going inside. So looking into this picture, you can see this joint 1, which is less inclined, joint 2 is more inclined, less inclined than joint 1, and joint 3 is going inside. But remember that on the left hand side, you are seeing the things in a 3D. In the right hand side, you are seeing the observation of joints in a 2D plane strain condition. How to convert from 3D to 2D, that also I will mention very briefly. So we collected the information of these 3 joints, the slope face, the trace plane, their dip directions, what spacing occurred, what is the joint length. They're giving at least some idea of persistence and non-persistence. And then we did some stereo plot. So from the stereo plot, as I mentioned earlier, this is a kinematic analysis. We try to get an idea which joint set is more vulnerable to failure. And that also helps us to ideate that what can be the stability issue in that particular location. But as I mentioned, that stereo net might not always give the exact feature, but it is fair enough. So how to draw stereo nets? Please refer to some books. There are very well documented procedure you can refer to. Now, what is the necessity of a 2D jointed rock slope model? As I was mentioning that on the left-hand side, you are seeing a 3D model, and on the right-hand side, you are seeing a 2D. Doing a 3D analysis is very computationally expensive. It requires huge resource. So many a times we do a 2D analysis to get the best sort of idea. And then if we find that, no, that is also not giving me the proper understanding what is happening in the field, then and then only we move ahead to 3D. For jointed rock system, it is enormously computational demanding, computational fund and resource demanding for 3D rock slope stability analysis. So 3-dimensional model for jointed rock slope definitely will predict more realistic result, but it demands more computational efficiency as well. Now, as I was mentioning, joints create the stress anisotropy. Hence, the failure mechanism in 3D will depend upon the direction of the loading, and it can vary from block to block because they're interacting as well among themselves. So to make our life a little bit simpler, we developed this 2D jointed model from the 3D field information. And when we do it for the first time, it looks very ominous to convert a 3D jointed system to a 2D jointed representation. But understand, there is nothing ominous in that. Whatever you have done or you do or teach in your engineering drawing course, where you talk about projection of lines and planes and projection of solids on your oblique planes and auxiliary planes, it is basically that thing itself which we do for creating a 3D model to a 2D joint model in the rock slope. So all these exercise what you carry out, finding the trace plane and converting or projecting the different joints in the 3D to the 2D over the trace plane. So that is basically a engineering drawing problem and nothing else. You just need to practice it to get properly the results. So let's say when we have these orientations, so we find out the trace plane over which we want to work and figure out how the slope face will project on the trace plane. If there are 3 sets of joints, as for this particular case study, how joint J1 will project on the trace plane, how J2 and how J3 will get projected on the trace plane for the concerned slope. So in that way, we move ahead, we create a 2D trace plane model from a 3D jointed rock system. And then we move ahead to the numerical model, where now we have J1, J2, and J3, the 3 joint sets over the trace plane. We create the boundary conditions. For the static analysis, the bottom boundary remains fixed from any deformation. For the same static condition, the vertical boundary that remains fixed from horizontal deformation, but it can be free in the vertical deformation because there can always be a vertical movement. There is some debate for especially jointed rock slopes that whether we should keep the bottom boundary completely fixed. Not necessarily. You can free it up to some prescribed displacement as well, but you cannot free it up totally. Otherwise, your model will run here and there like a rigid body, and you will not necessarily get the desired outcome from your exercise. For this particular case study, some geotechnical details are necessary. As I was mentioning, we have to find out the equivalent strength parameter. In case of rocks, the failure criterion which we use is not really the Moore Coulomb one. For the rock system, we use a criteria which is given by Barton and Bandis in 1990. It has the feature of a Moore Coulomb representation. It is tau equal to sigma tan phi plus some of the cohesive component, but the representation is a bit different. Here, the factors which affect the shear stress generated in the rock are definitely the overburden pressure or the normal stress. Phi r is the residual friction angle. Remember, it is not the peak friction angle as we consider for the soil, for the normal soil mechanics problem, because rock slopes or rock joints will move only when the residual strength is exceeded and not really the peak strength. The reason I will tell later in one picture. JRC is the joint roughness coefficient. You have to figure out from the test on the joint material. JCS is basically the joint compressive strength. So these JRC and JCS are the parameters of the joint. Phi is the parameters of the rock body. Now, how to find out residual stress? We need very tedious experiment for high strain experiment for that, but we always do not do that. We can still find out from the basic or the peak friction angle from such expressions, where peak friction angle in relation to a special type of test, which is called a Schmidt rebound hammer test, which can be carried out on a wet and fractured surface, as well as a dry and unfractured surface. And the combination of all these exercise, you can find out the residual friction angle with much less exhaustive experimentations than if you really find out residual friction angle directly from a shear experiment. Now, Barton-Bandis, this failure criterion is not a linear failure criterion like the Moore Coulomb failure envelope. So when we plot the shear stress and normal stress, the thin green line which you can see here is the Barton-Bandis failure envelope, which is a curved failure envelope. In fact, Moore Coulomb failure envelope is also a curved failure envelope, but for our simplicity, we fit a linear Moore Coulomb failure envelope over this and figure out what is the equivalent cohesion and friction from the Barton-Bandis assessment. So we have all the parameters of the Barton-Bandis assessment. We go to these equations, plot the Barton-Bandis failure criteria for the specific case. Then over that, we fit a linear Moore Coulomb failure envelope, and we get the equivalent friction and equivalent cohesion for the joint strength. Same exercise we do for the rock mass and the intact rock as well. In this case also, we go ahead in the same way and finally figure out the equivalent friction, cohesion, and the tensile strength. Someone may ask, why so much of equivalency? Because we want to make our life simple. Because if we want really to model with all these, we really have to go to the discontinuum system. And I think I have already made it clear how complex and bit difficult it might be. So as usual, we carried out the kinematic analysis of rock slope for our case study, and it showed that J2 is the weakest joint. Through this kinematic analysis, we understood that J2 is the weakest joint, and in this particular case, for the Garhwal Himalayan, for the Sikkim Himalaya highway, the joint J2 is the most vulnerable. That means there will be a sliding failure, a planar sliding failure along J2. But when we looked into the strength reduction technique, we understood that something is not really truly represented through this particular exercise of finding out the poles and then finding out the sliding failure through kinematic analysis, which says only one joint is vulnerable. Given that this picture, which is available, so here itself we can see that there is a wedge type of failure, and it is not really a single planar failure along one joint. So even though kinematic analysis showed one single planar failure, which is the most vulnerable, the picture doesn't reflect from the very site itself. So then we went to the shear strength reduction technique, considered all these joint sets, and used a particular method to figure out what can be the strength reduction factor to understand the failure condition. Now, as I was mentioning earlier, that this shear strength reduction technique, so this is a similar way how we find out the factor of safety. There is a slight difference. In factor of safety, we figure out the ratio of strength and stress. Here, we really do not do that. Here, we figure out the reduction of the shear strength parameter itself. So what happens is that we start from an initial condition. where we start with the available equivalent C and phi, which we have obtained from the previous exercise from Barton Bandis to the equivalent parameters. We get equivalent C and phi that represents an SRF of 1. And then we repeat analysis the same model under static stability by each time reducing the C and phi by a particular factor SRF, strength reduction factor. So we may reduce it by 1.2, 1.3, or if you want to increase, you may divide by 0.9, 0.8. And by this way, you figure out that in what manner these actual parameters can be reduced, under what coefficient value they can be reduced to such an extent that failure takes place. So in this particular way, we figure out whether the slope is susceptible to failure or whether it will be stable. For example, this particular slope, here you can see the critical SRF became 1.14, which tells that the value is above 1, but generally we say SRF less than 1.5 for static condition is susceptible to failure. So that means this slope is not really stable under the given condition, and exactly what happened at the site. There was a failure. Now, interestingly, if we see these dotted black lines, these are the joints which can be identified through which the failures are taken place through these shadings and contours. If we can roughly put these joints, so we have put J1 now over these particular diagrams, and then we are putting J2 over this particular diagram, and we can see from these contours that some locations are more prone to a J2 type of failure, J2 sliding failure. Some locations are more prone to J1 sliding failure. J3 anyways is going inside the rock slope. It does not affect anyways as such. So there is a mixed mode failure. The upper reaches of the slope is undergoing a sliding along the J1 joints. The lower reaches are going a sliding along, more prominent sliding along J2 joints. So that means what was given from the stereo net that only J1 was affecting or J2 was affecting as per the stereo net, that is not really true. There is a mixed mode type of failure. So at least the limit equilibrium analysis through the shear strength reduction technique, we get a much better view than what we obtained from kinematic analysis. That's what I was exactly pointing out earlier. Sometimes kinematic analysis might not give the true story. So in this case, we have critical strength reduction factor 1.14, and then we also found out the minimum factor of safety. Remember, as I told, factor of safety is strength by stress. We consider the entire material to be homogeneous. There is no joint set. In that case, the factor of safety is much higher. So which gives us an important understanding that if for jointed rock slopes, we do a homogenized type of slope stability analysis, then we may actually land up in a different sort of result, which might not be properly correct. So here, the minimum factor of safety was given as 1.5 from a homogeneous system, which basically indicates that the slope is all functioning well. There is no failure in the system. Whereas in the case of the strength reduction factor, where we consider the joints, we find that it is much lesser than 1.5 and the slope is vulnerable. Next, I will show the dynamic stability analysis, what we can do in such case, what information we can get. This is a case study from the Garhwal Himalayas, and this is again a highway which basically passes from Rishikesh to Badrinath, the National Highway 58. Again, on this particular stretch, we did some numerical exercise. Again, it is very important. It is a place where all our pilgrimage takes place. And again, being in the Garhwal and Uttarakhand Himalayas, it is very prone to rock slope failures. And again, this has an earthquake history. There are many epicenters around, and the scenario, as I described for the Sikkim Himalayas, also gets prevalent in this particular stretch as well. Now, when you do dynamic analysis, things become a bit more interesting in the sense that now we need to understand how the seismic wave passes through the jointed rock. We do dynamic slope stability analysis as well for the soil slopes, again through a homogenized system, but this presence of joints here make the things more interesting and challenging. Now, for this in rock science, you can use RS2 in its seismic mode using the explicit joint model, which I have described earlier. You can use both of them at tandem to figure out the dynamic stability assessment of a jointed rock system. There are some things such as Cauchy strain definition has to be given there. So those nitty-gritties you can always work out when you work with the actual software model. Interestingly, this RS2 has got very well developed over the time. It is still under development. It produces quite accurate result up to a strain of 1%. The 1% is still not so much nonlinearity develops in the system, but you can always do a rigid block movement through this 1% strain itself. Deformations, you can predict even in the lower strain limits, when we generally say that in very low strain there is no deformation, but that is not true in case of heavily jointed system. Always there will be micro deformations that also needed to be understood, because micro deformations accumulate to give the major catastrophic failure. Now, one question always arises, okay, fine, I am doing all these analyses and finding out what is the deformation in the rock slope system. When I shall consider it to be failing? Because in rock slope system, it might not always be the stress-based failure which governs, as in the case of soil slope. Here, deformation can also lead to a failure even before the stresses are mobilized. So in general, it is said that if there is a seismic event, and after the seismic event, if there is 50 millimeter or more of a deformation happening, so that is basically a limit beyond which we will say that rock slide will be triggered. So if that is lesser than 50 millimeter, 40 millimeter, we say that the stresses are not yet mobilized, rock slide has not triggered, but that might actually lead to a fall of few pieces of rocks and few chunks of rocks as well. Rock slide means entire mass of rock starts moving down. So when complete failure of rock slope is not of interest, then this method can be very interestingly used, but things have been evolving. This method can now be used even for fairly a good amount of rock slope failure, if not the complete failure. Whenever we do dynamic analysis, first of all, we do a pseudostatic analysis, which is a simplified version of the dynamic analysis. So I will just show this picture again from that Rishikesh Badrinath highway. So here there were three joint sets. J1 along the or towards the road was the most prominent, and this was heavily jointed rock system. So there were three specific sets of joint. So this was one J1, which is very slightly inclined. J2 is heavily inclined, it is very steep joint, and J3 is lying in between these two. Now, if you see, all these three joints are actually moving towards the road, and because of these road works, extension, excavation, all these slopes have become unstable over the time, and that has given impetus to study the rock slope stability in this area. So we went ahead in a similar manner. We did a stereo net projection, and interestingly, again, this stereo net projection showed us that joint J2 and J3 are the most active ones, and they will lead to a wedge failure through this J2 and J3, whereas the J1 was not showing any intersection. It was understood from the stereo net analysis that J1 is really not that influencing the stability failure. However, the picture said something else again, that there have been very much of evidences that there has been movement over J1 as well. So there were doubts over the stereographic projections once more. So we started with the pseudostatic analysis. Here we consider a factor called KH, coefficient of horizontal acceleration, which you can find out from your IS code 1893. You can find out KH, or if you have an earthquake motion, you know the PGA, the peak ground acceleration of the earthquake motion. When you express the peak ground acceleration in terms of G, in terms of acceleration due to gravity, you get KH. So if KH is 0, that is a static analysis. And what we do is that we use the same slope and subject it to higher and higher value of KH to see when the slope starts behaving or moving towards failure. So that gives us an understanding what can be the threshold of the seismic motion or seismic intensity that can happen at that region, which can lead to failure of such slopes. So for this slope, we carried out that exercise, and you can see that beyond a value of KH equal to 0.3, the SRF has reduced to significantly lower level, 1.1. So under seismic condition, we consider 1.1 or 1.2 as the limiting SRF, which can say that below that value, it is unstable, metastable, or if it is below 1, it is complete failure. So when we subjected this to maximum credible earthquake zone 5 as per the IS condition, so we found that the slope becomes quite unstable. So this might not exactly represent failure, the magnitude of 1.1, but as I was mentioning, it can shake up the slope, it can make it metastable, and any next event can lead to its failure. So when we looked into these two cases, 0.31 and 0.36, in both the cases, you can see that the specific failure lines are forming, but it is not like a slip surface. It is through the joints which is forming. For SRF 1.1, it is still on the greenish part. That means stresses are still holding. Whereas in the SRF, in the case of 0.36, SRF went to 0.97. That means it will already fail in case of that high motion. And interestingly, what we saw from here, that these two joints, that is the J1 and J3, are participating to control this failure of this jointed rock system, which was denoted as J2 and J3 from the stereo net, but not really, which is coming into fact from this type of analysis. Next, we move ahead. So pseudostatic again is more like a rigid body analysis, or we say that the rock blocks above the failure plane do not have that much of deformation and interaction among them. So then we move into the seismic motion utilizing the time history or the accelerations for that region. So we chose the Uttarkashi earthquake, which occurred in 1991. We got the acceleration profile. We did a Fourier transform to get the frequency domain response so that we can know what is the fundamental period or fundamental frequency of the input motion. And that helps us to understand in what way over the time the failure will evolve. So pseudostatic gives a direct failure or not failure condition. Seismic motion time history analysis tells you how failure will generate from its initial nascent condition to the final failure condition. So evolution of failure you can understand from the time history analysis. In this case, again, we prepared the model given the joints. Only thing we have to remember that in case of dynamic analysis, the boundary conditions change a little. The vertical boundary becomes a transmitting boundary. The seismic wave must pass through it, whereas the bottom boundary becomes an absorbing boundary, and the input acceleration, this acceleration needs to be given at the base of the model. So that entire model shakes up and there is vibration over, and you can find out acceleration, amplifications, all those things. In many cases, we use a compliant base because we cannot directly give acceleration. We have to give it in the form of shear stresses. So from the acceleration profile, we find out through the integration, we get the velocity profile. Using that velocity time history, VST, multiplied by the density of the material rho, multiplied by the shear wave velocity Vs, we find out the time history of stress. And that time history of stress we input at the bottom of the model. Now, since we are literally talking about natural materials always have damping. They do not allow every part of the seismic energy to pass through. They absorb some of them. And especially when the things are jointed, more absorption takes place. In general, in these cases, we use a 5% Rayleigh damping, and then we find out the Newmark's or Rayleigh parameters alpha, beta. These are some standard procedure which you can always use and learn from the even from the software manuals as well. When you do such exercise, when you develop the numerical model, you have to find out how much boundary you should use and how much mesh size you should use. So to find out the boundary, we generally, as mentioned, we give the acceleration at the base and find out what is the response at the crest or the top. So we always see that there is amplification. So acceleration at the top of the rock slope, this blue line, is having much higher energy than what you are having at the input. So that means amplification has taken place. So if you use very small boundary, the amplification gets affected. So the boundary reflects the wave, amplification becomes more. That is not a true picture. If you have very large boundary, you don't get that boundary effect. But if you have a very, very large boundary, your computational demand increases. And that also we don't want. Then you have to control the mesh size in such a way. There is a particular criteria called LK criteria, Lismer-Kulemeyer criteria, the two researchers who have given this proposition. By telling that, you have to make the mesh size such that one entire motion passes through that mesh element and you can record the effect of the entire motion. So there should not be any missing information developing, which can happen if you keep the mesh size very big. Somebody may say, I will keep the mesh size very small. You can always do. Your computational cost and demand again increases. So there you have to bring some optimality in boundary domain and in the average mesh size. So that exercise we do by varying the domain size, varying the mesh size, and finally figuring out what optimum values we should use. For this particular case, when we varied the base width of the model for various element size, we saw that around 90-meter model size things are converging. When we varied the element size, we saw that around 1.5 meter mesh size things are converging, because that model, what we are playing with, the entire rock slope is around 250 by 250 meter. So we have to bring these optimalities into the model. When the model is ready, you give the earthquake motion, and then you start to find the interesting responses. This is one such very interesting response which you can get from this RS2 modeling. So this is that rock slope which we modeled. So just to show, I am going back once. So this is the slope which we modeled with 3 sets of joints. We gave the earthquake motion. And in this particular case, what you are seeing here is the development of shear strain after the application of dynamic load. You are seeing these white lines in between. And if you follow these lines, those are nothing but the joints which we had given in the model. So this is J1, this is J2, and this is J3. So this J1, J2, J3, when these lines, white lines emerge, this means that there is no shear strain generated. That means they have moved away. So you now know that each block is moving away. At the bottom of the model, you can see some of these joints have slid down in a manner that they are sliding over the joint set J1. So sliding of this slope along the joint set J1, which was predicted by the pseudostatic analysis, is now very well captured through the deformation scenarios as well. So you can see all these are sliding down from its initial location towards the joint set J1. Now, one interesting question comes that which joint set will move? So we will answer that as well. So we plot a displacement contour of the slope when the seismic shaking has stopped. And as I mentioned, all these shear strain white lines which you are seeing is conforming to the joint set J1. You can see many of the joint sets have moved. But as geotechnical engineer, you have to say which is the critical joint set that will actually move, whether this will be the one at the shallow level, one at the deeper level, which one? There are many. So to do that, we start looking into the deformation response. So we have some monitoring points of the slope, A, B, C, D, E. A and B are on the crest, C, D, E, F are on the face of the slope. F is at the toe. Now, in this case, we are monitoring the horizontal displacement and vertical displacement with time. So as the earthquake motion happens, how the displacement is taking place at each of these points. And very interesting thing will come out from this plots and observations as well. So here, the maximum deformation of the slope which occurred is in the vertical direction after 6.9 seconds of the earthquake motion. And that very well matches when the peak of the earthquake motion is passing through this jointed rock slope. More interesting is that the post-seismic displacement is more than 50 mm. You can see when I draw this horizontal displacement line through 50 mm. So it is basically more than 50 mm in the points of B, C, D, and E. That means all these points are basically moving towards rock slide. So this upper part of the slope is going to heavily fall down if such earthquake motion occurs. So as I mentioned earlier, that 50 mm might be the limiting post-seismic displacement criteria, which can trigger the rock slide, and the same is happening here. If you notice here, around that region, there is a high concentration of shear strain release as well. So which indicates that this top part of the slope may fail. But then the interesting question, which joint set will be critical? There are many J1 joints, 1, 2, 3, 4, and many others. Can we find that? Which one will be the critical, whether it's the set 1, set 3, set 5, set 6? Yes, we can find that. For that, we need to plot the variation of average factor of safety along the joint. Why I am using the term average factor of safety? The factor of safety which we find in our conventional slope stability analysis for soil slope, as I mentioned, we find only one value of factor of safety, where we assume that over the entire slip surface or over the entire failure surface, the factor of safety is identical. That is not true for the rock slopes, especially for the jointed ones. That's why here I'm mentioning the term average and how it is different from actual point-wise factor of safety. I will show in the next slide. So what we did is that we considered various joint sets. So set 1, set 2, set 3, set 4, set 5, and set 6. What we figured out here as these black lines, and we found out the average factor of safety. Average factor of safety means over this entire failure plane, over these black lines, we selected points, find out the factor of safety, and then make an average over all the points over this failure line. Because as I mentioned, they keep on varying. When we plot the average factor of safety and we draw the factor of safety average equal to 1.1, remember that 1.1 is one of the steady limits that we consider for seismic rock slope failures as the limiting criteria. When we plot this line of 1.1, except for set 5, all the other cases, the average factor of safety is always greater than 1.1, which indicates that set 5 is actually the most vulnerable or potentially the most vulnerable one in all of these sets, and that will basically lead to the failure of this entire rock slope, especially the upper part of it. So if you do such an exercise, you can find out which is the critical joint set that can fail. The next interesting thing is that which portion of set 5 will fail. Why this becomes important? Because there is a basic difference between the failure planes of rocks and soils. In soil, homogeneously, we will consider it from the crest to the top or crest to the face. But in rock, especially in the jointed system, because the joints are present, the failure surface can change direction in between wherever the weaker planes of joints come into picture. That means each point will not have the same factor of safety. That means when we say that critical joint is J1 set 5, this will fail. Only a portion of it might also fail and not the entire J5 from the face or the toe up to the crest level. Can we find out which portion? Yes, again, we can find out which portion. So we again use some monitoring points, P, Q, R, S over this particular critical joint. And we try to see the variation of normal stress, shear displacement, and factor of safety. But now this factor of safety is for the points, and everything we are finding out how it is varying over the time. As the earthquake motion is happening, how the factor of safety is increasing, decreasing, regaining in strength, and then falling back behind the strength. And so similarly for the cases of other entities, we are finding out temporal variation, that is time-dependent variation of factor of safety at various points in the jointed rock system over the critical joint set 5. Now again, we draw the FOS of 1.1. So during the earthquake motion, the FOS should not fall below 1.1 to a significant amount of time. What we can see is that the FOS has gone down below 1.1, but not for significant amount of time. So during the peak acceleration, the entire joint set can start sliding, but it is not necessary that this sliding will lead to its complete failure. Whether it will fail completely or not, that is more guided by what happens at the end of the motion. So during the motion, this sliding can take place, and you can see that the shear displacement is remaining constant over the time, which means that the things are keeping on sliding, and with the case that entire system of that rock block can slide. But as I was mentioning, whether during the earthquake, this can go for certain time duration, for certain time instance below the factor of safety 1.1, whether that will state whether the slope will collapse or not, it is not correct in a wholesome manner. We have to see what happens towards the end of the earthquake. So once the earthquake ends, And we say that in the static scenario, after it, if the factor of safety remains below 1.5, then we say that it is more towards a complete failure of the system. And this thing happened for this particular slope section. You see that at the end of the earthquake, we have drawn this factor of safety of 1.5 line, and all the points P, Q, R, S, they are below 1.5 with the magnitude of P more closer to 1.5, which means that P might not fail and there might be failure in SRQ to the lower reaches. So there might be some movement in the lower part of joint 5, and then some other joint might fail in the other direction, which we have seen from the limit equilibrium pseudostatic analysis as well. So at the end of motion, complete sliding takes place as FOS is less than 1.5, but only up to the points S, R, and Q. The P1 upper reaches of the joint may not be that much affected. There might be some other slip line which can take place for complete failure. At the very end, we also look into the last interesting thing, which is called topographic amplification. So it is same as, it is nothing different as a simple amplification. So seismic wave amplifies. When you give a motion at the base, it propagates to the top. Because of the reduction in confining pressure, there is higher energy, so it amplifies. And this seismic wave amplification can induce instability. What becomes interesting in a jointed rock slope is that because of the joints itself, there might be local amplification which keeps on adding up. And that is what is called a topographic amplification. Some waves can reflect back from the joints, and they all can add up to give a very huge amplification, which might not have been the case if there were no joints in the system. So just as an example, in this jointed rock slope, which we were analyzing, this blue line you are seeing is the input at the base, acceleration versus time, and the green line is output at the crest, the top of the slope. You can see the accelerations have increased to significant amount. And definitely Fourier is nothing but a representation of energy in the Fourier domain. So Fourier power amplitude also increases. So anytime amplification will be there, but interesting thing, as I was mentioning, when we compare this amplification with joint and without joint, when you don't have joint, the amplification is much lesser than when you consider joints in your model. So these joints give this local amplification which adds up, and that leads to much higher amplification in the system. And that's when the rock blocks from the top starts dismantling, detaching, and falling off. So this amplification of seismic wave not only depends upon the path of travel, it also depends upon the geometry of the slope, the material contrast, because we have solid joint material, joints crisscrossing each other, and the internal fracture of the slope. So all these leads to topographic amplification. And there can be situations that because of this high amplification, the joints open up, and that can lead to the release of energy, and that can lead to the failure. So as mentioned, amplification of seismic wave in intact rock and jointed rocks are different. Jointed rock produce much higher amplification than the intact rock system. So when we do analysis of dynamic response of jointed rock system, this very important point we should never ignore. We should always find out the response in terms of how it should have been if there is a intact rock. What is the benefit? If you are able to figure out that there are some joints which are vulnerable, you can grout those joints, induce cohesive materials, make them more rigid, and then you can actually reduce down the topographic amplification, and the slope can become more safer, apart from external mitigations what you want to do. So from this entire exercise, what I have shown and discussed, we made a very nice contribution in 4 different aspects. We use the trace plane concept, the basic engineering drawing concept, to convert 3D things to 2D things. Otherwise, there are complex ways of doing that as well. This is an efficient mechanism which you can use. You probably, as a teacher, you always teach engineering drawing, and you can make use of that knowledge. We identified the failure surface of jointed rock based on the stress mobilization at joints due to the seismic load, as I shown from the shear strain diagrams. And then within the restriction of this explicit joint model that it can handle lesser strain, but we tweaked that thing to handle higher strains as well, utilizing the post-seismic displacement criteria and the factor of safety evolution over the time. And then we also captured the amplification in and of the presence of joints, and that showed us how the jointed rock slope is more vulnerable than an intact rock slope in case of seismic motions. So again, these are some of the publications which you can refer, which had come out from this entire exercise. Very nice work had been done. And with that, I will definitely acknowledge my earlier student, Amalesh Jana. So he is now a faculty at Montana State University, USA. So it was his work entirely what I have shown you today, and we gained so much of knowledge, and that was just from a MTech work. So that was an immense contribution which he had made during his master's times. So with that, I will thank you all for your patient hearing. And again, I will thank the organizers for contributing to the young and the ongoing faculty member groups. So through this faculty development program, I hope some interesting things I could convey. And as I mentioned the earlier day, you can always revert back to me now, later, anytime, if you want to interact further or for any other geotechnical curriculum things. So that will be all from my side. So over to the organizer. I hope I was audible.
Yes, sir. Yes,
that
sir.
I did not.
Yes.
Great. Okay. I since I was not hearing anything, I thought that in between I got disconnected. I kept on speaking and nobody could hear.
No, sir. Thank you very much, sir. And once again, thank you very much for taking this time and share your expertise with us. And we sincerely appreciate your presence and look forward to your future contribution and collaboration. Now this is open for the question discussion session. So participant, if you have anything, please ask. Participants are requested to ask the questions or any queries you may ask.
So as again, I will provide the slides to the organizers. So you can also share, and later also if they want to interact, that is also fine.
Hello, sir.
Hi, General.
Okay. Are there anyone having doubt? Dear participants?
Participants should be more vibrant in interaction, because this is the platform when you start interacting and it goes ahead over the time more and more.
Maybe they have exam, they are preparing for the exam.
Okay, no problem. So you can anytime connect me later. So
yes,
you have all my contacts and I